started on this session on planetary exploration. Our first speaker, Michael Saint-Guillain, will talk about robust operation management on Mars.
Okay. Hi, everyone. So, of course, it will be a study about scheduling, where I used to call it operations management, because here what we do is that we deal with activities that are performed by human beings instead of machine scheduling, which is kind of different context anyway. And we want to make it robust as well, because we care about uncertainty. So consider, for instance, this quite simple scheduling problem in which you have only 4 tasks. So each having its own attributes. Here, for instance, you see that task B cannot be performed during the afternoon. And you see also that task C is related with task A in a way that you can only perform task C between at least 1 hour and maximum 12 hours after the completion of task A. And so these are the precedence constraints or the dependency and so on. So it's a so simple problem. You can see that actually there is only 2 different solutions here. Either you go for that solution or that one. In the first solution, you can see that it's quite good because you can actually complete the entire project in only 1 operational day, whereas the second solution requires an additional day. So clearly, if you want to optimize the entire completion time of your project, you should a priori go for the first solution. But the thing is that whatever happens, what happens if you cannot predict with certainty the processing time of the task? For instance, let's say that I cannot predict the processing time of task A, and if we say that, let's assume that its average time would be of 1 hour, then you will have kind of a significant probability to exceed 1 hour, of course. A scenario in which actually the first solution falls in this scenario in a very catastrophic way, because here you can see that if A requires more than 1 hour, then task B will not be completed during its time window, meaning that we'll have to resume it or even maybe restart from scratch at the beginning of the second day. So you will require a second day. And at this point, when you complete task B and you want to start task C, then you will notice that actually it gets even worse, because this constraint here will not be fulfilled anymore. So in this scenario, it's actually the entire project that fails, because the solution is not valid anymore. So it's actually not a robust solution here, but if you look at the second solution, even if at first glance it didn't look so interesting, it's actually completely robust. So we can see that even for such a simple scheduling problem, assessing of the true expected quality of a solution is not a trivial thing. So here we formulate the core problem as a robust scheduling, robust single machine scheduling problem with random processing times. We put these job precedence constraints. We call sometimes dependency. We have time windows and minimum transition times. This, if you use what we call a 2-index flow formulation, you can formulate it as an integer program quite easily like this. So here, of course, since we are single machine, a solution looks like simply an ordered sequence of activities. And what you want to do, of course, is to find the a priori solution that maximizes its own robustness, subject to these constraints that actually define the solution space where you are searching for. These constraints are quite classical. So the flow conservation constraints here simply state that the solution should be in fact another sequence of activities. And here you have a bunch of constraints that are used to model the job precedence constraints. So at this stage, you should be wondering actually where are the time windows constraints and the minimum transition times and so on. Actually, there is no time dimension in this formulation, of course, because actually the time dimension is stochastic. So I would not state that this activity must be performed during its time window. Instead, I will say that I want to maximize the probability that those time constraints are fulfilled. Okay? okay? And actually, this is the meaning of the robustness measure here is to compute the probability that a solution remains feasible with respect to the time constraints. So before diving in the computation of R, here the robustness measure, we must state some operational assumptions, which are quite simple. Here we call it recourse assumptions. So it's quite natural. We will say that whatever happens, the activities remains performed in the same order than what was planned in the a priori solution. Then we say that quite naturally that actually the actual processing time of an activity gets revealed only at the moment you complete the activity, right? And finally, you would say that if, unfortunately, a job cannot be completed during its time window because of some unfortunate processing time, then the job must be interrupted and reprocessed, like restarted from scratch at the beginning of its next valid time window. If such next valid time window exists, of course, otherwise you fail, right? And the sequence is interrupted. So we use these assumptions, and in order to compute the probability of a solution to remain feasible, so first we should say that, of course, quite trivially, this probability can be expressed as the probability mass of all the succeeding scenarios. Of course, the problem is that we cannot compute this because of the exponential number of scenarios. But thanks to this operational assumption we just made, we can, instead of reasoning on each scenario separately, we can reason instead on the random variables. So here the random variable would be like this. So here PJD would be the probability that activity J requires D time units, right? And then we can start to think about that and to say, okay, first let's say that the robustness of a solution, so the probability that the solution remains feasible, is quite naturally the probability that each and every activities gets correctly completed. That's quite sound. And it is actually equivalent to the probability that the very last planned activity gets correctly completed, right? Because I just said in the operational assumptions that whatever happens, if something bad happens, if I cannot complete one activity, then the sequence is interrupted. So if I fail at completing B here, for instance, I will never have a chance to complete D. So that the probability that all this task or the project is correctly completed is equivalent to the probability that the last task is completed. And that probability here can be quite easily computed by summing over the entire horizon on this random function, which is actually here the probability that the very last task gets correctly completed. So here the random function P, J, and T is the probability that a task J gets correctly completed at a particular moment T. Of course, this computation depends on three things. Firstly, of course, the time window of the activity J. It also depends on the duration of J, which is the random variable here, and also the time at which I started J. Okay, the time at which I can start working on J, which of course is a random function as well that depends on the preceding task. So naturally, it depends on the completion time of the previous task, but also any minimum transition time constraints that we can have. So recall that the minimum transition time constraint would say that between the completion of one task and the start of another task, there should be at least some duration, some delay. Well, actually, the computation goes like this, backwards, and it's quite simple, except if you have those minimum transition time constraints, which kind of complexify the computation. And we actually show in the paper that if you don't have such minimum transition time constraint, then the computational complexity is quite good. It's pseudo-polynomial, and it looks like this, where n is the number of activities, and h is the size of the horizon. But So that's quite nice because I mean that's only thanks to the operational assumptions you made, right? Even if you have like exponential number of scenarios, you can still compute exactly the expected cost of the solution. But if you have at most one such constraint per activity, then you will fall in this complexity. And in a more general scheme, if you have more than one constraint like this on each activities, then you will fall in exponential complexity. So it's quite interesting thing. It's a theoretical limits of this computational framework. Say that if you have to deal with minimum transition time constraints or any constraint that looks like, maybe you should not go for this and go for like Monte Carlo sampling or sampling-based methods. All right, so that's all for the theoretical part. Now we jump to the application part. So we applied these results on a project organized by my university. So we went for a crew of 8 members, or PhD students and researchers from my university. You can see that people come from many different domains. And we stayed for 2 weeks in a research station owned by the Mars Society in the desert of Utah. This is a picture from above. And so, of course, the objective was to simulate a stay on planetary habitat, all right? So, of course, we had a lot of fun and so on. But, well, the objective was also to simulate science here because, well, you don't do research in such a constrained environment, such as a planetary habitat, the same way you do research in a university lab. So everyone came with 1 or 2 research projects. You can see that there are lots of different things, like from chemistry, particle physics, biology, botanics, pharmaceutics, and so on, including my project on operations research, of course, which actually consists in taking all these projects and model all these projects as scheduling problems. So I take all of these and put it all in a same big scheduling problem because, I mean, the problems are not independent, of course. They share a lot of resources. And then I optimized based on that, producing some schedulings for the remaining days of the mission. And then during the operations of the guys, then I would be like working around and reporting everything that happens so that at the end of one operational day, I end with an adapted problem that I can in turn optimize again to get planning for the remaining days. So just to say about the operational context, and we can apply that kind of techniques on a team of human researchers and so on. But more than the feasibility of the approach, what I was interested in is, and it's actually the aim of the paper, is to compare 2 things. To compare the results we obtain based on a classical deterministic scheduling formulation and the results we obtain based on the stochastic robust formulation of the problem. Of course, what we want to compare, given the solution, is the average performance or the average behavior of the solution in real conditions, right? So we must do simulation to simulate real conditions. But of course, the problem is then you realize that theory and reality is not the same. Especially, of course, when I arrived there, I realized that the problem we faced in place was quite different than the problem, than the theoretical problem I came up with. What's happening now? Okay, I don't know what's happening. There is still, the image is still on the computer, but I have no idea because the computer is still awake. There is still an image on it. It seems that maybe the projector is asleep, or I don't know. well, usually I'm quite happy to be the first guy to present. Always better than the last on the last day, you know, but well, of course, it comes with some kind of uncertainties. Okay, fine. Well, so of course there were a lot of difference between the problem we targeted there and the theoretical problem. I explained in the paper how we deal with that, but it's completely problem dependent. And it's maybe not so interesting here. What's more interesting is actually a problem that I'm sure we face in every or almost every case study is a problem of the unavailability of the data. This is clearly not problem dependent. It's the fact that most of the time, a huge part of the interesting data are not available. In our case, I mean, let's say if we want to optimize based on this stochastic robust formulation, then of course we will optimize, we compute a solution in light of some probability distribution, which are estimations, right? The probability distributions are provided by some human experts. But if you want to assess the true quality in real conditions of the obtained solution, then you must assess it through simulations that are based on the real probability distributions, right? Which are necessarily different because you cannot know the real probability distribution. What you always have are estimations. And it's actually not an issue. It's like a property of your problem. You will never have the real probabilities. So you have to deal with that, and it's actually not so I mean, it can be complicated, but in our case, we made it simple. We just went for generating real hidden probabilities and setting these probabilities as assumptions during the experimentations, during the simulations. So in 5 different contexts, we generated real hidden probabilities to be revealed only during the simulations, of course, right? I don't have enough time to explain all the 5 different experimental contexts. I will just talk about the last one, which is a context in which all the real hidden distribution probabilities have been generated in such a way that globally all the estimated probabilities overestimate the real probability distributions. So I think it's quite interesting because it's what actually happens. If you have to plan something to make some decisions, to come with a schedule, then if you are convinced that one activity will last for 4 hours in average, on the paper what you will write is definitely like 5 or 6 hours so that you mitigate the risk. So that's exactly that kind of situation. All the estimations, all the estimated probability overestimate in average the real probabilities. And we show that even this context, we can actually obtain with the stochastic formulation solutions that are in average 3 times more robust. That is, the solutions in average success in 3 times more scenarios than simulations, than solutions that were obtained with the deterministic model. At this stage, well, there is still a lot of things to say about that, but one important question remains is that what is the price of such robustness? Because if I come up with a solution that is 3 times more robust, but if it costs in terms of operational costs or scientific outcomes, I don't know, if it costs 5 times more than the deterministic solution, then maybe you can think whether it is useful or not. But here what we measured is that the relative difference between the solution obtained with the stochastic formulation and the solution obtained with the classical deterministic one were of about 7% in average in the relative difference in the solution's deterministic quality. So of course you can have, so here we multiplied by 3, but it's in this context, which is, I think, in my opinion, the more realistic one. Of course, in a context where all the estimations are underestimating, it's of course, way worse, but. Okay, there's still a lot of things to say about that. You should have a look to the paper, hopefully, and just a couple of words about further work and what I'm currently doing. So currently I'm trying to apply these results and these techniques to manufacturing process in biotechnology companies. And what I've come out is that maybe this can be useful for operations management of planetary rovers. I'd like to point at the presentation will be given by Chien, Agrawal et al. Tomorrow at the application track. And that's all. Thank you very much.
So I think we have
So the robustness.
If you had distributions with long tails, for example, then in order to be completely robust, what you might have to do is schedule one thing each day, because there's some chance that this thing can take very long.
Yeah. So. Well, actually, of course, you can have many different kind of distribution. I guess when you talk about distribution with long tails and so on, you talk about asymmetric distributions. The thing is that here in our computational framework, there is no problem with dealing with asymmetric or weird distributional functions and so on, because everything is discretized, and we consider the discrete probability of one distribution at one moment, so that anyway, even if you have weird or with very long tail distribution, the optimization model will, formulation will optimize towards like the solution that is the more robust, even if it implies maybe scheduling only one activity per day. Oh, no, indeed. What we did, yeah, I didn't have enough time to talk about that here. And if the slides were still here, I could have shown you my backup slides. But what we did is a B-objective optimization, actually. We were optimizing the scientific outcome, or the cost, the deterministic cost of the solution, times the probability of the solution to remain feasible. So we optimize. It's quite a simple way to do it, actually. Just the deterministic cost or scientific outcomes times its robustness. So we got this B-objective optimization. Otherwise, we could not talk about relative difference in the solution cost or relative cost if we were not optimizing as well the scientific outcome, indeed. And then you can come up with like some kind of Pareto front, which tells you which are the threshold you can.
All right.
Okay. All right. So Tiago Vaquero will talk about temporal brittleness analysis of task networks for planetary rovers.
All right. Let's see if that works. So again, my name is Tiago. So I'm going to present today the work on temporal brittleness analysis for task networks. Task network for planetary rover. This is the work that we've been doing at JPL. I'm going to start with some motivation. I'm going to describe what we meant by temporal brittleness analysis. We're going to use the case of the Mars 2020 salt types to kind of exercise the analysis that we do. I'm going to present the approach and some experimental results. So one of the main process on the Mars rover operation is to define a set of activities for the rover to execute during a Martian day, a sol. And that process requires a careful consideration of the activity's duration, dependencies, and temporal constraints. So, executing those activities in the Mars environment is quite unpredictable and uncertain. So that means that accurately defining the temporal constraints and activities is quite hard. So a traditional way to go around that temporal uncertainty is to add a lot of large margins to activity durations, which becomes quite conservative. Ideally, what we want is to deploy and design task networks or the set of activities in a way that is robust to any exogenous events or delays, so that to make it less conservative. So that brings us to at least start to define, as Michael was presenting, a way to define robustness. And a good thing is that there's a lot of interesting work in our literature, some from our own community, in which we can at least analyze flexibility and robustness. Some of the ways that we can do that is by measuring temporal flexibility, for example, by computing the aggregated time slack. The other way is just to compute the likelihood of successful execution, like Michael was presenting as well. The other way, also from our community, computing the risk of temporal constraints violation. This is all, a useful set of tools, right? But when we went to Planetary Rovers, we kind of felt that we needed more information about, what's going on with those, metrics, or at least with the values that we got from those metrics. In particular, we want to analyze what is the acceptable deviation of the nominal duration for each activity. What are the activities that are most brittle to deviation or delays? And what are the sources of potential brittleness due to temporal constraints? So this talk is in particular, we'll go through those particular questions. And the way we see this is more like a complementary work to those metrics that already exist. Specifically, our goal is to analyze and measure the degree of acceptable activity duration variations, such as the delay, within which we can successfully execute a task network or a schedule. In particular, on that process, we're going to identify and enumerate most of the brittle activities. We're going to map those brittle activities to the task network structure itself, so we can pinpoint and address undesirable levels of brittleness. So this is the kind of pictorial representation of what we're actually proposing. So given a task network, a bunch of activities, temporal constraints and dependencies, that's what we're going to be proposing. And the hope here is that we can enumerate and measure, how brittle each activity is, and put that in a ranking process. And then we're going to map that information, and we can say this is the most brittle, this is the second one, and blah, 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 and try to help out the designer to see what's going on. All right, so as the case study, I'm going to use the Mars 2020 salt types, which represents what we believe is going to be being executed during a sol. That plan, we're going to see other talks about this particular salt types from Mars 2020. But that plans basically have a start and end point of execution. We have a set of mandatory activities, typically between 20 and 40 activities. Each one of them we represent as having the earliest and latest start time. We have a cutoff time, which is the latest end time. We have the estimated duration, the nominal duration that we believe we're gonna have. We have a bunch of dependencies, what activity has to be executed beforehand and what activity has to be executed after that particular activity. We do have unary resources such as instruments and also energy consumption, but for this particular work, we didn't consider those resources. For that, because those constraints are in the network, in the task network, so we actually did a pre-process of the task network. We ran a particular scheduler that we've been working in our group so that we can sort it out, the instrument usage. For example, if we have an A, B, C, D, to E here using the same resource. We just ran the scheduler to decide the ordering in which we're going to use that resource, right? So we can explicit add ordering constraints to the task network, right? So that means we don't have any disjunction temporal constraints anymore. Great. So before I dive into the actual analysis, I have to bring, emphasize a few of the terms that we're going to use a lot. We actually have heavily used that in the analysis itself. So we're going to turn all those task networks into STNUs. That means we're going to have a set of time points, start and end points. This is the execution horizon. Each activity we're going to turn into 2 time points, require point, and a controllable or uncontrollable time point. We can represent all the start constraints over here and related to that. And time constraints over here, and then the duration, which is uncontrollable. Right? So if we were under an STN environment, then we can check for consistency, but because we're talking about STNUs, we have to go through controllability theory. So we're going to use that, and specifically, we're going to use a lot of dynamic controllability check for this particular analysis. Okay? So I'm assuming there's a lot of you are familiar with that, but basically we're checking, if the task network is consistent in any situation that arises in the external world. Great. So let me dive into this. So the low-hanging fruit here is to analyze where the acceptable deviation of the duration for each activity. So we propose an analysis called here ceteris paribus analysis, in which we're going to pick an element and we're going to set everything else unchanged. Let me explain this. So we're going to pick one activity at a time. And for each activity, we set all the other activities' duration to the nominal duration. So, and then we slowly kind of increase the uncertainty around that activity 1 duration, right? And then for each iteration, we check if it's dynamic controllable, right? Up to the point in which it's no longer dynamic controllable. Right? So we record that duration, and we do this for activity 2. We set everyone else to the nominal case. We do the same evaluation until the point it's no longer dynamic controllable. So if we keep recording all those durations, we can actually plot that into brittle durations. Here's one example of the task net that we use. And on the right side, you get just the delay in which it becomes uncontrollable. So from this chart, we're kind of ready to start to understand a little bit of brittleness. So if I pick the very first activity here, which is about 14,000 seconds, this is the brittle duration, right? When it becomes uncontrollable. This is just the delay in which it becomes uncontrollable. So with a tiny delay, that it's already break the constraint. So that gives a little bit of sense of this is a brittle activity. If you look at the other side of this chart here, there's this kind of huge duration for this particular task. The delay itself, it's also huge. The nominal duration is actually very small, so that means we can delay a lot. And that is less, let's say, brittle than compared to this one over here. I would say it's not brittle at all, right? So that gives at least the acceptable durations on the special case in which everyone else is set to the nominal duration. So going deeper on this, if we actually have some information about the duration, such as the min and the standard deviation, let's say from a nominal distribution, then we can actually measure that brittleness. And that's what we propose here. So it's basically the same approach, right, in which we pick an activity, we set everyone else to be in a nominal case, but we're going to use a sigma multiplier to kind of drive this kind of increment of uncertainty around the nominal duration. So this is our Z multiplier here, and this is our metric. We're going to do the same thing, keep checking the dynamic controllability until the point in which the Z is large enough so that it becomes uncontrollable. So we do that for every activity, using the sigma multiplier to drive that increment. And the intuition here is that the smaller our sigma multiplier, the more brittle the activity is. So to be a more intuitive way to represent this, which is the chart I presented before, is that if we do it 1 divided by Z, that we can say, this is the most brittle activity, and kind of enumerate within all the activities we have, right? So yeah, for this case, if we do that inversion, then it's just the largest we have, the most brittle it is. One quick comment here, because I was talking about the special case. On the special case in which everyone else is nominal, the good thing is that our sigma multiplier here is the upper bound. That means if we have delays elsewhere in the activity, that number is going to be a little bit lower, potentially. All right, so yes, it's maybe not always the case in which we're going to have this nice, one activity being delay and everything else is on nominal case. So to cover the case in which we have delays and uncertainty across the whole test network, we propose a Monte Carlo simulation to explore how our sigma multiplier would be affected if we had uncertainty across the whole schedule, right? So what we do here for each Monte Carlo simulation, let's say M, so we're going to follow kind of the same approach, but as opposed to setting everyone else to the nominal duration, we're going to pick a Y sigma multiplier that is randomly picked for each activity, right? So that creates a set that's randomly generated. So that's the first important information. The second one is that we have to pick the sigma multiplier, which makes the test network dynamic controllable as a start. Otherwise, we're starting in an uncontrollable state, so it doesn't make sense to analyze deep if it's already in a bad shape, right? So we do the same thing. We get our sigma multiplier for activity 1. We do the analysis until the point in which it becomes uncontrollable. Then we run, let's say, multiple simulations in which we're always trying to pick a different sigma multiplier for the other's activity. We did this n times for activity 1. We do n times for activity 2, and we keep going until all the activities are covered. So with that, we can basically plot the same thing, right? We can enumerate all the activities are super brittle, not that brittle, by the mean value of our Z. And what we see here is actually two things going on. So one is that no matter what happens with uncertainty across the network, some of the sigma multipliers are just flat. They're always the same, right? So we're gonna understand why that happens. And the second one is that we have a lot of variations. So if uncertainty is put it across the rest of the network, then we're gonna have our sigma multiplier being affected by it. So you see large variations. Cool. So in addition to our Monte Carlo analysis, we wanted to bring that information to the test network to kind of visual inspect what's going on. For that, we add a layer of information to the test network itself by adding for each activity the rank that we figured out, the sigma multiplier, our metric, the delay in which it becomes uncontrollable, the specified time window in which the user provided, and then if you run an all-pair shortest path, we have probably a tighter time window just to help out the designer to say, okay, maybe I put this too tight. We also do the same thing for the start time to see if it's also too tight. We present a number of dependencies, meaning like what activity has to be executed before and then has to be scheduled after. So, and then again, we layer that information into the test net. That's how you see the color codes over here. Right, so for the experimental results, we kind of selected about 9 test networks that are very representative of what the work will be doing. It varies from 18 to 46 activities. This is more or less the information when we translate that to an STNU. You see the number of nodes and edges in the STNU. Running the set paribus analysis, our sigma multiplier, we collect just the minimum one and the maximum one. So you see that for this particular set, it's quite brittle with a tiny, with small, modus multiplier, we're already kind of becoming uncontrollable. This is an example of those graphs. Sometimes we have a clear winner of brittle activity, and then sometimes we have this, like a large number of brittle activities in the test network. We ran the Monte Carlo, and then we map that information to the test network. And by doing that, we kind of observe 2 cases in which explain brittleness in the test network. So the first one is due to a tight user-specified execution time window, quite common. And the second one is due to a dependent chain. So and I will pick 2 cases in which that happens. So the first one is, this is a fraction of the test network in which just get that particular very brittle activity. So that's, for this one, is the top one, right? So this is a long drive of the rover. It's about 3 hours and 37 minutes. Given the uncertainty that we give that for that particular rover activity, if it delays about 9 minutes, we already become uncontrollable. And you see here, there's not other temporal constraint related to it, but just the time window in which that has to be executed, and some also for the start time. So it's kind of isolated from everything else, right? If you look at the first parables analysis, our sigma multiplier, it's very like almost isolated here with a high brittleness metric. Now if we look at the data from the Monte Carlo, this is the one right here. So if we add delays and uncertainty across the network, it's always going to break on that 9 minutes, right? So again, it's too tight of a time window. This also happens with activity related to tied to lighting requirements, in which you have to perform sensing at that particular time. Then if the uncertainty is too high, then that won't work. Right? The second case, it's when you have a lot of dependencies going on. So here, as an example, we got a sequence of 7 activities that depends on the same instrument. That is the remote sensing mass. The first 3 activities here are imaging activities with mass CAM-Z. They have their specific time window, right? But they have to occur before all those 4 tasks over there, which is related to NavCam. These have all the same kind of mean nominal case and nominal duration, but they differ in how uncertainty they are. Some of them, they have a high value for the sigma, right? And that's the case over here. So this one have a higher uncertainty related to it. It's on the 3rd on the rank. So that's a quite risky activity to put in this sequence because it's most likely to get delay, and then we're in trouble, right? So this is to prove that someone would have to come back here and then try to see what is that what we want, right? All right. So just as a summary, so I presented a method for analyzing and measuring temporal brittleness of task networks. We can pinpoint sources of undesirable levels of brittleness by analyzing and layering the data of the brittlenesses to the task network itself. Our hope is that we can provide information to designers to revisit, renegotiate with engineers and scientists, and potentially relax some of the temporal constraints that are already modeled. And we use that visualization to help out with that process. So I'm going to leave it with the general process that we did here. And this is our analyzer here. This is the output that we got. Yeah, that's it. Thank you.
Okay, we have time for a question or two. Yeah, here, let me give you.
So you decide on the ordering first to avoid the disjunctive constraints.
That's right. For activities that are related to resources.
Right. In your examples, it seemed like that the brittleness didn't arise due to the ordering in those examples, right? So that changing the order wouldn't matter because the tight user time window would still be there, right, or the chain of events would still be there. But do you think there are examples where maybe the ordering would matter to where it might be useful to do your analysis on different orderings and then pick the one that had the least brittleness overall?
That's a good point. Good question. I would say that if there was not a beautiful change like the one that you saw, right, in which the schedule will actually pick an ordering in which it will say would put in the beginning of the plan, and then there was a lot of things going on in the middle, and then we'll try another time to execute that particular task with that instrument later on. Then it might make a difference. So you might have a group of a sequence over here that is kind of disconnected with a sequence at the end of the plan, let's say. That could be, it really depends on where the scheduler decide to put those clusters of use of that particular resource. In the case, I understand, I totally agree with you that it doesn't kind of show too much if it's all kind of there, right? But if it's spread out, then I think it does matter.
Okay, let's thank our speaker again, and we'll move on to the final talk of this session. So our speaker for this next and this final talk here is Josh Vanderhoek, JPL, and he's going to be talking about Mars on-site shared analytics, information, and computing. Mike's not.
Do that. Okay, so now you can hear me, I can hear myself. So again, this is the title of my talk. I'm Josh Vanderhoek, representing all these fine professionals listed here. So the problem that we're talking about today is sort of scheduling distributed computation among a network of agents. So I've drawn a network of agents for you there on the right. These are heterogeneous agents. They have different sensing, mobility, and processing capabilities. Because they're mobile, they have a time-varying communication graph that connects them. So we're talking about changing bandwidths and actually disconnecting the network occasionally. We're trying to schedule a task network across all of them. The task network has several interesting properties. For instance, some of the tasks can be pinned to certain agents, so they're required to be executed here or there. Some of them are optional but rewarding. So these are the things that we would like to maximize the number of times we can do. And then some of them, all the tasks have dependencies. So we have a dependency graph representing our task network. And just to get, spoiler alert, sorry, but we present a mixed integer linear program that can solve this across the entire network, and we test it in a distributed system. So I'll be presenting both the MILP and the test results. So the two agents that we considered in our study were basically a lander, or a high-powered asset on the left, and then the little pop-up rovers on the right. So if you haven't seen them, let me introduce you to the puffers. So they are a small folding robot, and actually the wheels will fold up on top of the chassis, so you can stack them in a payload bay. And the idea is that when the lander touches down, it sort of begets this network of puffers onto the surface, and they can go and do some science independently or collaboratively. Our assumption here is that because of the ongoing investment in better computing architectures, that the lander will have something like a laptop, and these puffers will have something like a Raspberry Pi. And that's just notional. It's not too important for the thought. Okay, so the mission that we consider is something like this. So, lander touches down, he ejects a bunch of puffers, and then they move either in a swarm or independently towards a feature of interest which is too risky for the lander to touch down near. So we have this is, I guess, a collapsed lava tube from the moon, right? So the puffers will then make their way to the edge of the crater and begin potentially suiciding off the edge to landing in the bottom. And if any survive, we can then get very nice images of the bottom of this lava tube and relay them back up through a communication chain to the base station, which will then communicate it to Earth. What you see already is that we've got highly heterogeneous sort of compute abilities. The base station can be a support node for these little guys as they're moving around, doing some autonomous planning for them. We also notice that there's intentional and unintentional network failures or disconnects. As I fall down into that cave, I can't expect to communicate immediately. I have to wait for the network to come back alive. So our scheduling has to take all of this into account. So to do that, we borrow something from delay-tolerant networking called a contact plan. So what a contact plan is, oh wow, okay, sorry about the gray bars. But what you're seeing here is a timeline. So time stretches off to the right, and these are 4 agents, and there's these little gray bars which denote the availability of a communication window between the agents. And so if in traditional networking, if you wanted to transmit from, say, the orbiter all the way down to the puffer, which we're pretending is in the bottom of the cave, you have to wait all the way to the right when there's a bent pipe relay all the way down to that rover. But in delay-tolerant networking, you can exploit the fact that you can do store and forward networking. So each node in the chain takes custody of the data until the next link comes alive. And so again, this is just another constraint on our scheduling problem in that when we do distribute the tasks and we're shuffling the data around, we have to be aware of these communication windows. The task network that we consider is relatively simple. It's just 2 chains. The top chain starts with taking an image, localizing yourself with respect to some map perhaps, planning your path for the next step, and then executing the drive commands. And then the bottom chain is the sort of the lucrative science one, which we can only do when we're near a science target. But In the event of an asset being near a science target, we'll prioritize the bottom chain, subject to the fact that we need to complete all the things on the top. Okay, so to belabor the point, network of assets, software or task network, time-varying communication topology, and we would like to map all of those tasks across the time-varying communication topology to all the assets to get everything done. This is the Rosetta Stone for our MILP. So at the very top is our reward function. This is the state variable x is basically all time slices, all agents, and all tasks. So there's Boolean variable, it's true if an agent is computing that task at that time. And then we multiply that times the reward for that task, if any. So that is here. We have a number of sort of intuitive constraints. I think the most important ones, of course, are that you cannot complete a task or start to compute a task until you've received all the data that's a prerequisite for that task. And you can only have that data by computing it yourself or receiving the result of a similar computation from another agent. Yeah, don't focus too much on that. Therein lies madness, but we explain this fully in the paper. So this is the situation that we've described so far. So if you do solve the MILP, you're solving basically a centralized version. You need to know the entire network, you need to know all the agents' tasks, and you need to have a godlike view of it. So moving this towards a decentralized solution, which is what we're actually trying to build here, we divide the problem into sort of a sense, decide, act, right? So gossip, plan, and act. So in the gossip phase, everyone's broadcasting the tasks they need done, they're broadcasting the local network conditions until everybody understands the whole network. So I've drawn that here. Every agent has a picture of the whole network and all the tasks that need to be completed. This is sort of the shared world approach, right? There's a couple of caveats here. We understand that consensus is hard. We had a great discussion with the reviewers about how consensus is hard. We would like to talk to you more about consensus if you're interested in this problem. So we tested this distributed gossip plan X cycle in simulation and hardware. And I'll present some of the more interesting cases. So the first one here is a movie just like the one before. We're going to assume that we know that this puffer is in a science zone, this puffer is in a science zone, and that this guy is planning some motion. We a priori know he's going to move back towards the base station. And so what we're going to see is that, we can get this to play, there we go. So here's our 4 agents. We're sweeping across the timelines. You can see data moving around the network. The first thing that happens is the base station helps Puffer 1 with his autonomous householding tasks. So he's actually relaying the information to him. And the second thing that happen is that Puffer 2 and 3 start loading up Puffer 1 with their science data so that he can actually do a data mule action and carry it back to the base station for them. Very exciting, so it works. And again, you can see the discretized time. These little colored pairs indicate transmissions and so on. Later tonight at the demonstration, you'll be able to look directly at this time window. It's right on a nice screen for you, and we'll recreate some of these things for you. We then tested this in a physical network. So we implemented all of this on these Raspberry Pis. We gave them a GPS unit, and we carried them around the Mars yard. We had a RViz-based visualization, which you're seeing on the right, and we built a custom timeline visualization, which you see on the left. There's a lot going on here, but as I said, if you stop by tonight, you'll be able to see it and tear it apart. We executed these task networks, and the whole thing operated for about 3 hours. We'll publish the demo code for you at this site. It's not up now, but we're very tired. We'll get to it. Here's the video. So you can see that we have some agents that are moving around the Mars yard. They're being carried by my intrepid co-authors. And we have a base station there, which is basically a desktop on a cart. And what we've done is we've geofenced a few areas in the Mars yard. So the blue zone is a science zone. Any node in the science zone will then try to activate the optional but rewarding tasks and schedule them across the network. The red zone is a sort of communication block, right? So this could be the edge of our crater or something else. And we did this over and over again and found some interesting cases which are very hard to see, so I'll just highlight one of them for you. This is what we call the assembly line. So to set this up, so Puffer 1 is in a science zone. 2 and 3 have high bandwidth connections because they're closer, right? So we use the distance to determine the bandwidth. And then we're trying to get all the data back to the base station. That's this archive task, right? Puffer 6 is out here sort of alone, but he at least has some tenuous connection to Puffer 1. So what you see is that here's Puffer 1 in the science zone. The first thing he does is transmit some data to Puffer 6, who does some autonomy tasks, the householding tasks for him. So basically, he's offloaded all of the stuff that he has to get done to somebody else. so that he can focus on gathering science data. The rest of his timeline here is basically gathering science data and transmitting it through this chain back to the base station. What's most interesting, I think, about this is when the data gets to Puffer 2, Puffer 2 takes over that pre-processing task and generates the data product that needs to be archived, which is then relayed back to the base station. So it's an assembly line. Here's an image. OK, I'll take care of it. OK, now I'll transmit it back to Earth. Again, please stop by. We have a bunch of these examples we'd like to show you live. OK, so to repeat myself, what we've done is we've presented a MILP that can do distributed scheduling across a heterogeneous network of agents with a time-varying contact plan. That's it.
Okay, we have time for some questions. Get a mic back to you.
Is the planning process on the little puffers as they run around, is that essentially the like solving the MILP that you were discussing?
Yeah. Each one does the broadcast, solves locally, executes their part of that plan.
So don't you have any capacity constraints on the amount of data a buffer can gather from the other buffer before releasing to the base station?
So caching constraints or memory constraints?
Yeah, because I didn't see in the...
Yeah, we could have put that in, but we did not. We were dealing mostly with just 400, 480 by 600 images notionally. We should and will.
Other questions? All right, well, thank Josh again.